Hi, welcome to a live tour of the LIGO-Hanford Observatory. My name is Joey Shapiro-Key. I'm a newly associate professor of physics at the University of Washington, Bothell, which is not far from the UW Seattle campus and just over the mountains from the LIGO-Hanford Observatory. Our tour guide today will be Fred Robb, who is the former head of the LIGO-Hanford Observatory and currently serves as the Associate Director for Observatory Operations, which includes the LIGO India project. So he'll hopefully tell us some about that. And then we're also joined by Cassidy Issa, who's in the control room. So you can see a live view of the observatory control room. There's Cassidy. She's a science educator at the LIGO-Hanford Observatory. So we're very happy to be able to connect with both of them. As you have questions, as we're going through the tour, go ahead and put those in the chat. Cassidy will be monitoring the chat. So questions that need to come up right away, she'll let us know. And otherwise, we'll save some questions for the end. I think that's all we need to know. Fred, go ahead, take it away.
Okay, thank you. So I'm going to pull up some pictures and video to show you. And let's see, I'm going to minimize this screen so that I can see what I'm showing you. Okay, I don't want to be here, so let me escape. That was from testing earlier. Okay, now we're going to start. So welcome to Hanford Observatory. A lot of LIGO is outside, and outside we have poor connectivity. So I'm going to give you the outside scenes in video. And then inside on the experimental floor, a lot of the chambers are closed up, but I have good photos of the construction time. And so that will have to suffice for showing you what the equipment looks like. So first of all, the elevator version of what LIGO is all about is that the LIGO team works to explore the most extreme regions of space and time and the most extreme forms of matter in the universe. We do this by detecting the ripples in space-time called gravitational waves that are produced by black holes and neutron stars that we observe in some of the most violent events in the universe. What can we learn from these waveforms? I think it's a good illustration of what you can pick up is having seen the recovered waveform from our first detection of gravitational waves, I could immediately tell that we had observed a collision of two black holes that were much, much larger than we possibly expected. And so I'll just walk you through how I knew that. First of all, in the early part of the waveform that we picked up, this is called the in-spiral. These are when the two orbiting objects, which in this case were a 29 solar mass and a 36 solar mass black hole orbiting each other. The phase evolution of this signal as the amplitude and frequency rise are telling you about a combination of the two masses and the aligned components of spin, meaning the component in the orbital angular momentum direction. If the orbiting black holes have some spin perpendicular to the orbital angular momentum, then there'll be precession of the plane of the orbit, and then you'll see amplitude modulation. You don't see it here because these black holes didn't have a precessing orbital plane. Then you see a frequency where suddenly there's a highest frequency in the waveform, and that frequency occurs basically just as the two objects, compact stars, are touching and merging. And so basically, knowing that that frequency was about 250 hertz, immediately labeled these things as having Schwarzschild radii that were bigger than we were thinking of, and labeled these as roughly 30 solar mass black holes. Typically, X-ray astronomy had revealed evidence for black holes that were in sort of the 10 to 20 solar mass range. So these were much, much bigger than we expected. And then the ring down frequency and the Q of that ring down tell you about the mass and spin of the final black hole. So at this point, when you get to the merger, you basically know just about everything there is to know about the source, including how strong it is. And so when you actually measure how strong it appears, you're measuring something that tells you about the luminosity distance. How far away is this event? In this case, 1.2 billion light years away. And that is a number that is got broad error bars due to the signal to noise of the event, but is still good enough. We put a lot of work into calibration. And so for higher and higher signal to noise sources, we can get more and more exact distances to the source. And that's important for cosmology. Another illustrative event was GW 170817, which was a merger of two neutron stars in August of 2017. In this particular case, what this illustrates is the importance of a network of detectors and the ability to communicate events that become the foundation for multi-messenger follow-ups of events in the case where there's matter involved. And so this particular event was detected by the LIGO-Virgo network of 3 detectors that allowed us to triangulate to a point in the sky that was consistent with gamma rays picked up by integral and Fermi GBM. And that allowed us to send information out to other astronomers who then were able to rapidly, once the sun went down, search through that error box and find the new source, which was the kilonova produced by the merger of these 2 neutron stars. Eventually, 70 optical and other electromagnetic wavelength observatories would follow up on this, involving about 1/3 of the world's professional astronomers. And that told us many things about the supernova and an important test of Einstein's theory, which is that we were able to confirm to 15 decimal places that the speed of gravitational waves is equal to the speed of light. So how do the detectors work? We're touring the detectors. The basic idea is pretty simple. If you imagine a gravitational wave originating behind you and coming up at your computer screen, and if you imagine that computer screen in front of it has a sheet of space, two-dimensional plane of space, and in the upper piece of that, we have a circle of dots in space. What would happen when a gravitational wave penetrates that plane is that it would create a distortion that is quadrupolar. Basically, it'll stretch one axis and shrink the other. And that could be, say, on the trough of the wave here. I'm sorry, the crest of the wave here. Then you go back to 0, and on the trough of the wave, you get the opposite stretching and shrinking axes. And so to determine that a wave has passed, what you would need to do is have some inertial masses that mark off the center of the circle and 2 points 90 degrees out on the circumference. And a good way to read that out is with a laser interferometer. And so the basic Michelson interferometer was invented in the 1880s. What we've done is figured out how to adapt that to the search for gravitational waves. But the basic idea is that we set up a Michelson interferometer, which has equal distances as we've set it up between a beam splitter and 2 mirrors, and no light falling onto the detector. But then when it's imbalanced, so when the arms are equal, no light reaches the detector. But when the gravitational wave distorts the arms, it takes longer for light to travel the longer arm path, and that allows light to reach the detector. And it's basically the phase shift that produces that. And the amplitude of the gravitational wave that is illustrated is then the difference in the 2 arm lengths over the average arm length. And that quantity is traditionally called H, the gravitational wave strain produced at the detector. So what does LIGO look like from the ground? You're looking at the corner station, and now we're starting to look at the outside of what's called the X arm. It goes under a fire road and then heads out eventually to what looks like an end station, but is actually the mid station here. And as we zoom in, we can see the end station further out. Then if we pan around to the Y arm, okay, so the Y arm coming out of the corner station has this feature here up to a building. That's a 300-meter cavity that's used for trying to reduce the effects of quantum noise. And then you can see the mid station and the end station out on the Y arm. So that's the layout of LIGO from the outside. As an optical configuration, it's a bit more complicated, and obviously one can unravel the layers of the onion of complication more and more, but this basically in this diagram shows you the fundamentals. So we're looking for effects that are millifermi type displacements on a 4-kilometer baseline. And so, you know, a wavelength of light is half a micron or a micron. And we are having to basically measure things that are on the order of 10 to the minus 19 meters. And so one step one does is to try to narrow the optical feature that you're trying to measure. And we do that by in each arm. So here's the beam splitter. The 4-kilometer arms in LIGO are Fabry-Perot cavities. These store the light for on the order of 100 bounces. And what that does is it makes the feature of a dark fringe 100 times narrower. So now you have an optical resolution of 10 to the minus 8 instead of 10 to the minus 6 centimeters. And then you need a lot of signal to noise, a lot of contrast to see very small motions of the fringe. And we do that by balancing a lot of power in the arms of the interferometer. So you can see this little label that says on the order of 800 kilowatts eventually. We're going in our next observing run for 400 kilowatts in the arms. So how do we do that? We start off with a laser of order 100 watts. And that comes through a system of optics up to the beam splitter and then gets built up in the Fabry-Perot cavities. If the two arm lengths are kept equal, light doesn't go in the direction of the output arm down in the figure. It goes back toward the laser. And we can capture some of that light and send it back in for another measurement. The measurement's over when the light does not go to the detector, but goes back to the laser. And so we can repeat that. And we call this power recycling. And typically we shoot for about 50 recycles of each photon of laser light. And that's done by this set of cavities that I think you can see me pointing to over here, these three mirrors. And it winds up that that trick can also work if any signal is starting to emerge. You can use another recycling cavity, this one called the signal recycling set of mirrors, to push the signal back into the interferometer. And you can use this to tailor the sensitivity of the interferometer as a function of frequency, depending on how you set the reflectivity and the spacing of those mirrors. And then finally, what you would really like to have as a light source is a beautiful disc-like thing in X and Y, and something that in the Z direction looks like a perfect sinusoid. And that's not what comes out of lasers. And so we have to do some massaging of the light. And so you see there's an input mode cleaner, and you send in perfect light and you put it on real mirrors, and some dirt comes back due to sort of 1/10 of a nanometer distortions of the mirrors. And so we have an output mode cleaner that cleans that up. And so that's the basic optical configuration of a LIGO interferometer. Now, something I'm going to tell you is that noise, quantum noise, comes into the interferometer because dark is not totally dark at the photodetector. And so those vacuum fluctuations come in through the detection port back into the interferometer, mix with the light coming out of the laser, and create two of the quantum noise problems, one of which is phase noise. And our signal is a phase measurement. The gravitational wave is a phase measurement. And the other is an amplitude noise, which is that we get imbalances in the forces of radiation pressure striking the mirrors. And so the one effect at high frequencies, the mirrors appear to move due to phase fluctuations induced by vacuum fluctuations. At low frequencies, the mirrors really do move because they're recoiling from the fluctuating radiation pressure due to vacuum fluctuations. And so we do a technique called vacuum squeezing to try to beat the quantum noise down. And that was a new thing in our third science run. So that creates some extra mirrors, and they're shown basically here. There's an extra 2 chambers, and that's the origin of that 300-meter cavity that I showed you from the outside, which was basically a filter cavity associated with the vacuum squeezing experiment. So the overall beam tubes, this is a picture of them in construction. We see that we have a long spiral welded tube. It's got a concrete cover for protection. We shoot for a trillionth of an atmosphere operating pressure to reduce mirage-like effects of the laser propagating through residual gas, causing the mirrors to appear to move when they do not. And it's pretty easy to pump the air out, but air has some condensables, CO, CO2, water vapor, and to remove them, you have to do a bake out. And so these are pictures of the insulated beam tubes. Here's a portable power supply that ran 2,000 amps through the tube. You do that for about a month on each 2-kilometer tube segment, and that reduces these condensables, gets them out of the vacuum system. To show you we're right now outside entering a concrete cover, and we have a test section that was set up for various testing and proving for the beam tube construction. So this is not an actual beam tube module, but a model that was created for it. We just zoomed in on the 3mm stainless, which is very soft. We're now looking at the stiffening rings that keep the tube from collapsing. And then here you can see the spiral weld pattern. These were just to get a certain number of spiral welds on a tube. We didn't actually use that spacing. We used about a 3-foot spacing for the spiral welds. And here are a system of bellows. When you bake out the tube, you have a thermal expansion issue to deal with. And so you need some bellows to allow for thermal expansion to be taken up. But you also need rigid mounts. And these were just small mounts that were built, but you need a way to support the tube and hold it in alignment with those soft bellows in place. If we go inside the corner station building, this is a photo I took quite some years ago that shows the basic arrangement of chambers. And if I can take my cursor and lead you, this section of tube moving left to right is basically along the Y arm. And this section of tube that appears to be downward, but is coming towards you in the picture is I'm sorry, that's the X arm, the other was the Y arm. We see a big steel chamber, and that's the one with the beam splitter, and there's a hallway behind that. That's where the laser originates, and there is a small hallway off to the left of that big chamber, and that is where the signal is processed, is pulled out of the interferometer. Just to give you a feeling of height, John Warden, who ran the contract for all the chambers and was later the operations manager for the site, he's about 6 foot tall. And so that just gives you a feeling for the size of the chambers we use. Inside these chambers, there are a number of layers of vibration isolation. So we have 2 layers of active vibration isolation inside the vacuum chambers. And so this piece would be mounted to something rigid, but then we isolate to stage 1, and then another cascaded layer isolates to stage 2. And then we would attach optical components to stage 2 inside the big chambers. And so that's what would appear up in the dome of the chamber. And then we have 4 stages of suspended masses, the last of which is the actual payload mirror that we are trying to isolate. So if you imagine one of the mirrors at the 4-kilometer ends, that would be the bottom mirror in the leftmost photo. And then you see something above it that looks identical. And what you're seeing above is an identical blank of synthetic fused silica as the mirror. And if you look to the top right image, you can see that it's connected at the top mirror or the top mirror blank. There is a fused silica fiber that is attached to the mirror, and that fused silica fiber makes the two mirror blanks that you see in the diagram of the photo to the left, makes them a single monolithic structure. And the reason for this is to reduce the effect of the KT of thermal noise that appears as random motion in any system at a finite temperature. And so the way we deal with this is we design the structures so the actual resonances of, say, in this case, the suspension, or in the case of the mirror blank, the internal degrees of freedom vibrating of the mirror, we design those to be outside of the observing band, but even the wings of KT can cause problems. And so to reduce those, we have to use very low loss materials throughout. And what that does is it narrows the resonance associated with those and sucks the energy out of our observing band. And so we typically look for losses on the order of a part in 10 to the 8 or a part in 10 to the 9 per cycle of oscillation of the materials in the last stage of our supplied pendulum. There are two more stages above this mirror, which is called the penultimate mirror, and you can see one there. It's got some steel music wire that supports the penultimate mirror from this stage, and then there's another mirror stage that gets hooked up above that. In this slide, you can see the actual assembly of the system to give you some orientation. So this is the vibration isolation that will go up into the dome of the big steel chambers, and then the suspensions and other optics hang below. And here's a close-up to show that. Finally, we have a system using green light to lock the system, to lock the long arms. In the meantime, the operating wavelength is 1 micron, and that is operating out of the corner station, locking up all the pieces of glass in the corner station to a fixed orientation. And then a process is used to basically bring the arms which are in resonance with the green, to transfer that resonance over to the main laser. And this is just a picture of the main laser system with a couple of amplifiers. So the main laser is in the box. That's a relatively low 1 watt laser system, and that's amplified by these two stages up to 100 wattish levels. Are there any questions about this?
Right, what questions do people have so far? You can put them in the chat. Or if you have your mic set up, you can just ask a question.
Well, we can move on and see if any questions do occur.
Yep, feel free to drop stuff in the chat if you have questions.
Yeah. So the one other feature that is new to the fourth observing run, 04, that we're preparing for, that'll start in March of this year, is that in '03, we went to a form of vacuum squeezing that allowed us to transfer quantum noise from the relatively high frequencies where we wanted to increase our ability to measure distortions of neutron stars by matter, or get finer measurements of the mergers of black holes and neutron stars. And so to set the stage, the types of frequencies we measure in LIGO are, we start to pick up one of these compact binary stars at frequencies of about 20 cycles per second. But from about 50 or 60 hertz up to a couple of kilohertz, we're dominated by the phase noise in the interferometer. And so to reduce that phase noise, we employed vacuum squeezing in the third run to basically reduce the thermal noise and push the H bar omega noise into the push the quantum noise into the radiation pressure. And we could get away with that because we had other noise sources at low frequency. So we were essentially sweeping the quantum dirt under the rug. However, that ultimately limited the amount of improvement that we could make at high frequency. And we have work to do to try to improve the lower frequency components of the signal, get more resolution below 50 hertz. That opens us up to much more massive black hole systems. And we've seen evidence for black holes up at 100 hertz and above. And so we want to start to explore that region more. To do that, you need a type of squeezing called frequency dependent squeezing. And what that does is at high frequencies, it allows you to squeeze the shot noise or the high frequency quantum phase noise into radiation pressure noise up at frequencies of above 50 hertz. But above 50 hertz, we're not sensitive to the radiation pressure anyway. So if we increase it, that's fine. We're mostly limited by phase noise. If you go below 50 hertz, now we are seeing the motion of the optics above phase noise. And at those frequencies, we really want to squeeze the quantum noise out of the radiation pressure into the phase noise. And so the thing that allows us to do that is to take our vacuum squeezer and bounce the light off of a cavity that has a resonant frequency in sort of that 30 to 50 hertz region. And that allows us to get one sign of squeezing at frequencies above that filter cavity characteristic frequency and the opposite sign below. And so that allows us to get squeezing to basically benefit us across our observing band. And to do that, there's a lot of extra optics. And so there are two new chambers, there's a new building, all to accommodate frequency dependent squeezing. And what you're seeing is the chamber, a view inside the chamber in the corner station building, which is showing one end of the filter cavity. And here is the squeezing, the in vacuum squeezer itself. And it's called, it's an optical parametric oscillator that's used to mix the vacuum fluctuations. with a signal that is coherent with the input laser that reads out the test mass frequencies and allows you to vary the phase of that correlation. And then there are some other optics that make up a tunable mode matching system to get the light without scattering or with minimal scattering to reflect off that filter cavity. So that's an added thing, and that's really the main worry now, is to get our system up and working with the big improvements from vacuum squeezing in the next 9 months. So that brings us back to the control room. You're seeing a static shot of the control room. So I'm going to stop the share and turn it over to Cassidy Issa with a live view of the control room, and we'll take questions. Well, maybe I'll start by telling you a little bit about some of these screens. So obviously there are a lot of things to look like. To give you a feeling for the complexity of LIGO without having to read the 25,000 documents that describe the detector, we have basically about 350 servo systems that take all of these many pieces of glass and orient them in space at fairly precise positions. So what we call a coarse servo mechanism in that chain has sub-nanometer resolution, and then we go down to sort of sub-millifermi resolution in the servos. And there are about 350 of them that control various pieces of glass and lasers and vibration isolation equipment in the detector, and quite a choreography to go from the state of uncontrolled motion of mirrors that are suspended by threads of glass and have mechanical cues approaching 10 to the 9, and getting that all to settle down to precision where you can actually detect these small things. So we have a lot of components that are monitoring this. A central one in the center of the front wall. So if you look at where people at their monitors are facing, they're facing the front wall. And that top screen is showing you an actual spectrum of the output of the interferometer live. And so that red trace that you see is the live state of the interferometer right now. I'm not sure exactly what they're doing to it. I think they're still making the transition to nominal low noise. And so we see that as various steps in that computer-generated choreography is going on, that signal will start to settle as we're talking. There are a number of screens on the right-hand side of the front wall that are used to diagnose vibration sources. And so we display bands of frequencies of seismometers that have various names, like the earthquake band, the traffic band, the machinery band, et cetera, that follow what are the disturbances measured on the ground. We measure wind speeds and other things on the sidewall. We have screens for those. There is a screen in the complex on the left side of the front wall. Some of those screens are just telling you states of the interferometer or auxiliary servos, but typically there's a screen up there that shows you basically a map of the world listing the most recent earthquakes. And when a new earthquake occurs of sufficient magnitude, you'll see it show up there flashing, and the machine will be thrown into a state that is lower sensitivity than the observing state, but more robust to ground vibrations. And so depending where the earthquake occurs, we have some number of minutes to try to save the controlled state of the instrument, which can save us a significant amount of time, downtime, because if the earthquake throws the machine out of having all the cavities locked with light in them, it takes quite some time to bring it back. So those are some typical monitors. If Cassidy can pan over to the left side wall.
And Fred, do you see there's a hand up from Jesse? Do you want to ask a question?
Oh, very good.
Yep.
Right.
So what's the question?
Well, thanks. So first, I'm a faculty member at MIT, so I hear from my colleagues all the time about the science that's going on at LIGO. But on the operations side, I'm curious whether you have any audio feedback. Certainly when presenting to the public about your results, you listen in to what the gravitational wave signals are. Is audio used by the operators in any way to kind of listen into how the machine is performing?
Not right now, but very often people listen to the machine for cues as to how it's behaving. And so when it's in a routine state, especially if you're making a lot of transitions, all you hear is a racket. But it's often used as a diagnostic to cue into things that are transients that occur in the noise. And sometimes it's quicker to pick them up and try to correlate them with what's going on by ear and using your eyes to read signals on various display monitors. And so, yes, we do.
Thank you.
There's also a question in the chat here. Do you see it, Fred? Or how long does it take to reach the low noise condition before starting recording data?
Yeah, that varies, and I don't have a good estimate of what it will be in the next run. And it partly depends on why you went out of observing mode. So if you don't need to realign the machine, it can be rather fast. Still, you'll be down for, on the order of 20 minutes. If you really have to do a full alignment, and sometimes, you got to do it more than once, you could be looking at an hour. If something's gone on the fritz, like you've blown an IC somewhere, it could take quite a bit of time to track this complicated system down and find that and cure it. So the timescales vary. I would say it's never less than about 20 minutes or so. When we go into 04 with the brand new squeezer system, I'm expecting it'll take a bit longer to find all the little tricks to speed up that part of the operation, but we'll see.
Great. And then you wanted Cassidy to pan.
Yeah, it's flipped for me as it is for you guys. So tell me if I'm going the right way or the wrong way. This way?
Wrong way.
Okay.
Yeah, okay, so the top far leftmost screen is a very important screen that we also look for. I think two of the most important are the front wall center one, where the spectrum is displayed. When something untoward happens, you would see everybody in the room suddenly raise their eyes to that screen. The one on the top left is showing you some history of what's going on. And if I could find my share screen button, here it is. I can actually show you a snap of that screen. Yeah, here's a snap of that screen. It's called SenseBond range. What this is doing is every minute we get an update to the screen, which displays the neutron star binary inspiral range that we could detect. And I'll tell you what that really means in a second, over the last 24 hours. So the origin of the x-axis is now at 0. And then basically 24 hours ago is on the far left of the horizontal axis. And then in megaparsecs, excuse me, but astronomers refer to these as God's units. Physicists are more comfortable with light years. A light year, a megaparsec is 3.26 light years. So multiply these numbers by roughly 3 and you get the range in millions of light years. And the curves show you in red for Hanford and in blue for Livingston and in purple for Virgo, what the ranges looked like and what the lock segments were in the last 24 hours. And you know, if we're in an observing run, this is a screen I would be checking first thing in the morning, last thing at night, before I go to sleep, to determine if I should go to sleep, and you know, throughout the day to see what the behavior of the system has been. Right now we're in a mode of commissioning, and so there are various different things people are trying to do, so it's not upsetting necessarily if we're not all the time showing, you know, 120 something megaparsecs of range. Other questions?
We do have a new question in the chat, which is how many people are typically on shift?
Yeah, so it takes one person during an observing run to be monitoring the instrument. Typically, a number of other people are doing work at any given time during an observing run using data from the instrument, but it takes one person to be available to operate the instrument. We've now gotten good enough with a lot of, or I should say, in the just before we started the 03 observing run in 2019, we were getting good enough that we could operate remotely. So that person could actually be off-site and monitor and have control of everything in the control room. And we were using that so that we could start to rely on alarms and whatnot to allow the operators to actually be working on building the next upgrade rather than spending all of their time watching the screens. So we have automated a lot of the processes of identifying error conditions and alarming people so that they can do other work in the meantime. And that process will continue. We've also have a lot of people in the science collaborations that support the operations of the interferometer, who again have done a lot of work to make a lot of the monitoring automated, so humans check in on things or they get alerted when there's a problem, but they can spend more of their time thinking and less of their time, you know, just keeping the thing running. And that's an important investment that we continue to make throughout the various collaborations. as you can see from the number of people in the control room right now, it is the best seat in the house for LIGO. Nothing quite compares to the visibility of signals and whatnot that you have in the control room, and the ease of asking somebody else a question is not to be neglected. I should say that during observing runs and even in off times, we maintain a channel of communication with the 2 other observatories or 3 other observatories that are running on the network, so that you know, if there are issues or even planning things to be done, they can be done. For instance, we may be detecting a building error state. You know, something is going to go wrong soon because we see behavior of a particular one of these servo mechanisms starting to get a little wonky, and it's going to need some attention, or there's something else we want to do, but because of the network observing, we don't have to do it right now. We have other nodes of the network in good shape. You don't want to take your machine down, but sometimes that these problems accumulate at a number of the observatories, and then at some point you reach the conclusion, why don't we take all the machines down, fix these things, and bring them up so that we can best have, you know, maximize the amount of calendar time that we have 3 or more machines observing on the network. Any other questions?
If people are interested in visiting the control room yourself, I'll say if you're in Seattle for the meeting, there will be a 1-day bus trip out to the Hanford Observatory next Wednesday. So it's just after the end of the meeting. And you can get on a bus at the Seattle campus. It will take you out to the observatory. You'll get a tour, including into the control room there, and a box lunch along the way. And then the bus will come back after the tour. So just a 1-day trip next Wednesday. There's a couple of tickets left for that if you haven't signed up and you want to. Is anybody on the line already signed up for that trip? Okay, if you want to, you can do it through the registration system. Thanks very much to Fred and Cassidy for being our tour guides. It looks like it might be lunch break in the control room too. People are getting up for lunch break. So thanks everyone for joining.
Yeah, there's actually a seminar they're going to.
Oh, they're going to a seminar. Okay. All right, with Shane. They're going to hear about Lisa then.
That's right.
Yeah, great. They're going to hear about the space-based observatory for the 2030s. All right, thanks everyone. Thanks so much, Fred. Thanks, Cassidy.
Bye-bye.
Have a good rest of the day.
Bye, guys.